Welcome to Samadhan Life Science. Today we will discuss about a very important topic from coordination chemistry, crystal field theory. So let's first understand the CFT in short. So if we have a octahedral complex with a central metal atom M and these six ligands, then during the formation of this complex, these ligands approach to the metal atom through this X, Y or Z axis. For that reason, the degenerate d orbitals in this metal M get split into two different energy levels. So the d orbital situated exactly along the x, y or z axis, that is dx square minus square y square and dz square, gets higher energy, and the rest of the three d orbitals go to lower energy, dxy, dyz and dzx. So now these lower energy d orbitals we will call them T2g and Eg for the higher energy d orbitals, and this difference between energy is delta O, octahedral splitting energy. Now, each electron in this T2g orbital has energy minus 0.4 delta O, and each electron in Eg has energy plus 0.6 delta O. So now if I want to calculate the total crystal field stabilization energy in any complex, we have to consider all the electrons situated in T2g and Eg. Plus we have to also consider the pairing energy if there is any paired up electron. Now this delta O splitting energy depends on the incoming ligand. So here I have given a series of ligands, and these earlier ligands have lower delta O. We will call them weak field ligand, and these last ones have higher splitting energy, higher delta O. We will call them strong field ligand. Now let's take an example of the six system. So T2G Eg. So if the incoming ligand is weak field ligand, so this delta O is smaller. So I will put the electrons, 6 electrons from D6, 1, 2, 3, 3 orbitals in T2G. Then for the fourth electron, I will go to Eg. So this electron will rather go to higher energy than pairing up, because here pairing energy is greater than delta O. Then the the 1, 2, 3, 4 and then 5 and the sixth electron then again will come to T2G to pair up. But if the ligand is strong field with higher delta O, so Eg and T2G has a larger energy gap, then the electrons will go to 1, 2, 3 to T2G, then 4, 5, 6, because they will stay in the lower energy and get paired up rather than going to higher energy, because this delta O is greater than pairing energy. Now see, for the weak field and strong field ligands, the number of spin in the complex is changing. So for weak field ligands, there is higher number of spin because the electrons are unpaired. So these are high spin complexes. And for the strong field ligands, the electron gets paired up, then go to higher energy. For here I have put 6 electrons. If there is any 7, then that will go to Eg. So this is a low spin complex. Now let's take example from your previous year question. So the question is the magnitude of CFSE in this hydration complex for these 4 different ions. So water is a weak field ligand. So all the complexes will be high spin. Now let's take these ion one by one. So first one is manganese 2 plus. This is a D5 system. So T2G and Eg. So T2G 1, 2, 3, then 4, 5 go to Eg. So let's calculate the CFSE. So 3 into minus 0.4 delta O plus 2 into plus 0.6 delta O. This will be 0. Now the next one, manganese 3 plus, which is a D4. So here 3 and here 1. So the CFSE will be 3 into minus 0.4 delta O plus 1 into 0.6 delta O. So this will be minus 0.6 delta O. Let's take the next one, Fe2 plus, which is a D6. So 1, 2, 3, 4, 5, then 6. So T to the 4 Eg2. Here CFSE in the same way will be 0.4 delta O, and for Fe3 plus D5 system, which will be similar to this one, so T2G3 Eg2 and the CFSE will be 0. So let's see now, Mn2 plus is greater than Mn3 plus, but Fe2 plus is less than Fe3 plus, which is our option B. This is the right answer. I hope you understand. Now let's go to the next example. So calculate the spin only magnetic moment for this cobalt aqua complex. So again, water is weak field and cobalt here is 2 plus. So cobalt 2 plus is a D7 system. So T2G, let's draw this. So Eg and T2G, right? So 1, 2, 3, 4, 5, then 6, 7. So total unpaired electron we have to calculate for calculating this magnetic moment. So here 1, 2, 3. Now the formula to calculate this magnetic moment is mu, magnetic moment mu is equal to root over n into n plus 2. What's n? N is unpaired electron. So here root over 3 into 3 plus 2, and this will come around 3.87, and the unit will be Bohr magneton, bm, and the question also asked in bm. So if you see any question related to magnetic moment of these coordination complexes, use this formula root over n into n plus 2. Easy, right? So if there is any unpaired electron in the complex that you will get from the high spin or low spin, then the complex is paramagnetic, that will have a magnetic moment positive value. And if all the electrons are paired in the complex, then mu is 0 and the complex will be diamagnetic. I hope this clears you and clears CFT for you. Thank you for watching today. See you in the next video.